And welcome, mindsetters, to this session of Learn Extra Live. Hope you guys are ready. You've got your pens and pads out and you're going to make some notes. I'm Ty and I've got Iti here who's going to be taking us through today's session. What are we doing today, Iti?
Today we're doing volumes
All right.
of common solids and shells.
All right.
The likes of cylinders, pyramids, all that. Yeah.
Okay.
Yeah.
So, Mr. Iti, while you make your way across the board, I'm going to tell the mindsetters what they need to do.
Yes.
Mindsetters,
Great.
make sure you get onto the page, chat to me, www.facebook.com/learn extra. Let me know what you guys are thinking. If you're lost in me, if you need help, post. And yes, it's the same drill. Yes, it might be a holiday, but we're still here to help you and help you learn. And yes, I will be giving away a Casio calculator and a labeler, so make sure you get on the page and talk to me. Best post wins. And I want to send a quick shout out to Liberty. Thank you for sponsoring the show. And this is where we continue. So, Mr. Iti, take it away.
Thank you, Ty. Greetings to our viewers out there. Yes, today we're doing solids, their volumes, and I'll just trace back and also make sure that we recap on their surface areas. So our common solids are typically the prism, the pyramid, and the sphere, or some of the other regular polyhedrons. All right. So I will also discuss, very important, the scale factor. The scale factor, in as far as it affects an object one-dimensionally, two-dimensionally, and three-dimensionally. So that's equivalent to that. I'm talking about the length, the area, and the volume. So typically, if I double each length of my cube, what will be the eventual volume compared to the original one? The same with the area. I will want to know what will be the area that results if I double the length. What will be the area compared to the original area? All right, so I'll also discuss, volumes and surface areas when a solid is truncated, which means it's been cut in the middle with with one plane, for instance. All right, so let's go straight into it. Volumes of solids and shells. Now, here I'm going to look at it moving from a prism right through to a cylinder. Now, the picture I'm painting here is basically saying, from a prism, if you keep increasing the number of vertical surfaces, your vertical rectangles, you are going to, if it's a regular base area, you're going to end up with a shape that is a cylinder. So I'm taking it from the bottom right to the extreme end, which will be a cylinder. So if I'm looking at a volume of a prism, I'm going to use the base area. Okay, so that the volume will be the base area multiplied by the height of that cylinder. And here, of that prism. Here we are talking about upright cylinders, upright prisms, not ones that are tilted or something. All right, so if you have the height as h here, and the base area there, obviously in this case we've got a triangular base area, so we know how to find the area of a triangle. The area of a base of a triangle is half its base times its height of that triangle. So you would have to be given the dimensions of that triangle to be able to work out what is the area. All right. So another way of looking at it, let's say this is the volume now. The base area times the height. So if you had a square base or a rectangular base, then your area, like we said last week, will be just the base times the height of that base rectangle. Then you would have to multiply by the height of that prism. So this is a rectangular base prism, and you could have a hexagon base, a pentagon base area, and you would have to get the area at the base and multiply by the height. So it's all the same. And if we continued with that up till we get so many areas that add up. Let me just cut out just one area that I'm talking about here. So if you imagine that you have got an infinite number of those strips, small areas going all the way around the cylinder. Going all the way around, they will actually form the surface area of a cylinder. So again, the area of the base is now pi r squared. In this case, the area of the base would be pi radius squared. So that would be a circle of radius r, let's say. And that would be our height. So that's what you would have. Again, we multiply by h. So this is easy to remember. You just have to find the base area and multiply by the height. Just a reminder now, in terms of the surface area, we said if we wanted the surface area, we would simply slit that prism. We'll slit it with let's say with a knife all the way down vertically and open that up, and we would see a whole number of rectangles that you have to add up. But the perimeter of these, of the base area, simply has to be multiplied by the height, and that's what gives you the surface area. So for the surface area, we would take the perimeter, and multiply that by the height. Get that spelling right here. Right, so we'd have to multiply that by the height of the prism that you have. So that now applies again from the simple triangular prism right through to a cylindrical, to a circle base cylinder. Okay, so yeah, that's basically what I would have liked to show about that one there. And we can move to another one. Let's see. Now we can move from a pyramid. Our common solids is going to be the prisms, the pyramids, and regular polyhedrons. Okay, so now we're moving to the pyramid. Now, notice what I have here again, moving from the two extremes. If you move from a simple pyramid, which is called, in fact, there is a name for this one. It's called a tetrahedron, especially if all the sides are equal. Tetrahedron. Okay, so you will notice that the base area is a triangle. And as you move on, you will now have, if you wanted the volume of that, now come back to it, you would have to, maybe I should take it from the cone, because from the cone, we know that the volume is going to be a third of the base area. That's R there. So the base area, which is pi r squared times the height. So what is happening here is, if this pyramid was uniform, in other words, its apex was right in the middle, you would actually have a very nice uniform. The areas would be the same all around. But in this case, because the dimensions may not be the same at the base area, you'll have to take them. Remember what I said last week? You'll have to get the net. For instance, you would have to find, okay, in this case, you still have to say, what is the area of the base? So you take the base area and you multiply by the vertical height to the, let me show that vertical height from here right to the apex. So this is the height to the apex. I think I have to just take you 2 steps back. We talked about the area of a cone last week. And I think we said the surface area of a cone is going to be, I think we said pi radius, and we multiplied the, times the slanting height. Now, this is what we call the slant height. So that was the surface area. Some of you might say, well, how do you get to that? Quickly, if you think of the perimeter at the base, the perimeter would be circular, and that means the perimeter there would be 2 pi radius. Now, we always want to take those small triangles. All right, so if we were to cut a cone and lay it out, this is the kind of surface we would get with the small triangles adding up, something like that. Depending on how many they are, then if they are equal, you would have to use that perimeter, because now each of those base, remember how we find, undo that. Let's just take it back. Okay, a bit of a mess. Yeah, let me undo that. Let's do that, yeah. So what you want is to take all these areas, all the small areas, add them up to give you the surface area. So all those areas, we will find them by saying half the base times the height. And we know that the height is that slanting height that we represented there, like that. Now, think of it, this is a result of stretching out a circle. We had a circle base, and this therefore becomes 2 pi r. So yes, we can add up all those areas, all those small areas, and in the end, they should give us half h is common, half and h are common. Now we get the sum of the base, which means each of these small lengths here of a triangle. Now, if you add up all of those base dimensions of a triangle, they will then give you, let's have half h outside there, but the sum of that, because we know it comes from the perimeter of a circle, we had a base, the circle as a base, okay? So now we can have 2 pi r as the sum of all those base, base length of the triangles. And there you can see the 2 canceling out. That's why we should have used L, by the way. I said we are going to distinguish this here. This should be L. Right, let's mark it as such. So we've got base times height, or slanting height. So now you have pi r times the slanting height. So now you know where this one comes from. I thought I should just trace it back and help you there. So easy to remember again. And where are we now? Let's see. There was a pyramid, from pyramid right through to a cone. So obviously the other ones where you've got a triangular base and a rectangular base, you would have laid them out exactly the way you laid out the one of a prism. Let's just take, for instance, a rectangular one. A rectangular base. So you would have laid this out like I showed you last week, so that you have that base area and the 4 triangles that connect up at a common point, which is the apex of our pyramid. And of course, what I've been writing here, you will notice it excludes the base area. Now, you would have to include it if it's a closed cone. The same with the cylinder, you would have to include, like I showed you last week, what I call a net, the net surface area. All right, So you'd have this area 1, then this would be the same as the, let's say, of course, this dimension here would be the same as that dimension. So that area, if we call it A2, that would be A2 as well. And this would be A3 and A3. So you'd have to add up those surfaces, those triangular areas to make up the whole surface of your pyramid. So that's exactly what we did with a cylinder, right? I said we moved from the simple case of a triangular base right through to a circular base, which we call a cone. All right, so thus far, are there any questions coming up also?
No,
Nothing
not
at all.
yet.
It's so
no.
dry today, yeah?
It's pretty quiet, but
All right.
we'll see. We'll see.
I guess, yeah, we can go for an ad break.
Okay,
Right?
so
Yeah.
mindsetters, you heard
Okay.
from Mr. E.T. It's a bit, you need some more questions. It's all good that you guys are saying, yeah, we're here with you, but you need to post up those questions. It's so important. But for now, we're going to see you after this ad break. And welcome back, mindsetters. Hope you had a nice little break there. You did whatever you had to do. But now you're back, you're focused, you're paying attention, you've got your pens, pads out, and you've got your phone in front of you so you can talk to me on your Facebook. That's what I need you guys to be doing right now. Chatting to me on Facebook. I'm loving what you guys are doing right now. Keep on sending in those posts because I need to give these away, this awesome calculator and this labeler. So make sure you post. But for now, this is where we continue, and Mr. E.T. is going to continue. Take it away, Mr.
Thanks again, Ty. Greetings once more. Now we've done the pyramid, we've done the prism. Let's move on to something that will lead us to a sphere. If we take regular polyhedrons, what I've listed here is a tetrahedron. This one is made of triangular surfaces that are equilateral triangles. And this one, a cube, it's made up of squares, as you can see, it's got the base area and it's got a height which is the same as the dimension of the square. All right, so if this continued and you imagined right at the end, remember now, for this regular polyhedrons, from the center of the polyhedron to any of the apexes, the distance is the same. So if we had a center there, the distance would be the same to the individual apexes, all of them. They have that property. And now, if you imagine that this continued until you have a sphere where you have a center, and any line that you draw to the surface of your sphere is actually going to be the same distance. So there is that property about it. And yes, of course, even the adjacent sides must be equal. Like we had here, that side is equal to that, and all the sides are equal from apex to apex. All right, it has to be the adjacent apexes anyway. So that's what we are saying about a sphere there. This is radius r. Now, we want the volume of that sphere. You would have to do a bit of calculus to really understand how we end up with this expression. This expression is an expression for the volume, 4/3 pi radius cubed. Okay, so that is the volume of a sphere. But then we can split it a bit. If you look at it, it looks like it's made up of two parts. So this volume, you could split it and say it's 3/3 pi r cubed plus 1/3 pi r cubed. So someone already can see that this is like having a cube of dimension r like that. And basically you take that, what would be, obviously we needed that factor pi there. Okay. But end of the day, what I want to point out here is that you've got pi r cubed, and that is added to the area, the volume of a cone of height r. If this was the height, remember how we find the area of a cone? We said a third of the base area times the height. So this would be the radius r, and if it had the height r, that would be the area of a cone. So the area of a sphere is more like a compound, the volume, a compound volume, just taking a cone and a cube, but now that cube must have a factor of, a scale factor of pi anyway. So that's r times r times r, which gives you r cubed, and you can just multiply that by pi. So I'm just trying to help you remember the formula itself. It is a compound volume. So that's what you have. Right, and if we move on, the surface area, if I can just recap on that as well. If we look at a sphere in particular, the area of the surface we said is 4 pi r squared. Again, this, you'll have to know a bit of calculus to be able to see how we come to that kind of formula. We don't have enough time to do calculus. Anyway, you'll have to wait until you do it in grade 12. All right, so that's the volume and the surface area of a sphere. Right. Now, a thing called a scale factor. On a one dimension, simply if I say I've got a length that is 2 and I say double it, so you're simply going to say 2 times 2 equals to 4. So if that was 2 meters, then I now have 4 meters. So that's pretty straightforward. The scale factor is 2. Scale factor equals to 2 in that case. And you could have halved it or used any other factor. Now, if you can imagine now an area, let's move to the case of surface area, let's say. You had an area that was 2-dimensional, obviously. Let's say take a square of dimension x and x, and we decide that we are going to double the sides of this square. So what you'll end up with is this side doubled becomes 2x, and if you double this side, you end up with 2x again. So now that is the area that you will have in the end. And this one is pretty obvious because you could actually say, well, this new area has got 4 equal blocks, that come from the same. But now, how do we show that? If you had length times length as your area initially, now what you have is the new area is equal to the length has been doubled. So we do exactly that. 2L times 2L. Okay. So in that case, we end up with 4 times L squared. So this was L squared there. So for any area, even if it was a rectangle, you would have to say, let's say this was L1 and L2, those lengths have been doubled. So you'd have to put it in exactly the same way. So what do I mean? If we had a rectangle now, and you had length 1, length 2, what you call the length and the breadth. So the area would have been L1 times L2. Now, if I say to you, double the length of this rectangle, you would have to say the new area will be double each and every one of those lengths, and you end up with 4 times the original area again. So I'm sure you notice that 4 times the original area. 4 times the original area. So now what do you notice about the scale factor when you're dealing with area? You end up with the scale factor squared. Okay, so 4 is now your scale factor squared. All right. So scale factor, when it comes to area, that's how it affects, that's what it ends up being. So we can move on to, even if it was a circle or anything, it would end up with a square scale factor. Now you might say, what about a volume? Let's take a simple case again of a cube. If our cube had, let's say, length 1, length 2, and other length, let's call it L3. So that would be our cube, and our volume would be L1 times L2 times L3. If we then say magnify this by a scale factor of 2 or a scale factor of 3, I think we've been using 2 too much, so I'm going to pick on 3 now. So if our scale factor is equal to 3, so all I'm saying is all those lengths, you are going to get them, let me go downward, just to buy space there. All right. So if we get 3 times that length and 3 times that length, we would end up with a volume that sits like that. All right, so you can see that there is your small cube at one corner, and you can pack a whole lot of similar cubes into the bigger volume. And let's get a pen. So remember, this is what we have here. So look at the big box, the one that I've dotted, and your new volume becomes 3 times L1, 3 times L2, and 3 times L3. So you end up with 3 times 3 times 3, which gives you 27. 27, L1, L2, L3. Now this part is the original volume, the volume that you had before you scaled up the sides. So what do you have? Your volume becomes 27 times the original volume. So this is the new volume. It looks like too big, but that's what repeated multiplication can do of the same factor. All right. So I think I've clarified the issue of scale factors. Yeah, when it's volume, it's simply going to be a cube of the scale factor. Okay. Okay, let's see if we can move to another section. I have decided to talk about truncated solids. Truncated solids, by that I'm referring to, if you had, let's start with a prism. If we had a prism with a square base, for a start, and we decided that we're going to cut it. Let me just show you one side of this. If I look at it from one side, I will see that rectangle. Now, if I decided that I'm going to use a sharp plane to cut across this prism, let's say on that line, that is my new plane that I used to cut right across there. So that's what you will see. And So you would actually see two portions of this, where you have this volume and the upper volume. Now the question is, how do you find a surface area of that truncated prism? If I just chop the top half and threw it away, out. Now I'm left with this prism, which has got now a slanted height. How do you then find the surface area of that? So you now have, notice that you now have different heights now. There is a height here, let's call it height 1, and on the other side, you've got another height, let's call it H2. Because this is a square base, I only have to deal with those two heights, and I cut it perpendicular to one of the surfaces. I could have cut it, so that it's at an angle to all the surfaces, but made it easy, just that one. So what you then have as a surface area is, if you lay it out like we did before, you will have a square at the bottom, and you will have one of the sides coming out nice and perpendicular, as a rectangle there, and the opposite side with H2, the other one with H1. And what you then do, if I gave this base as a square, I would say this is, say, X and X. So that is still X there. And now you have this one side to deal with. This side obviously is the one that I've shaded here. You can see up front, now it looks like a trapezium. For the other side, you suddenly have a trapezium that sits like that. Okay. This trapezium will therefore have, let's see. In fact, let me get my trapezium to face in the other direction there, so that H1 corresponds with H1 there, because I've laid this out, and H1 there, H2, H2. Now, if you have a net like that, it should be easy again to say, I know the dimensions of the square, I know H, and I still have X here. I will know that area. I will know that area as well, if I gave you the height H1 and H2. And is that now? All right, let's see. Cool. Yeah, so what you have there is that these areas can still be added, if I'm talking about the surface area. The only one that is now a challenge is the slanting surface area. You will then have to say, I need this length. So you'll have to find this slanting length. Okay. So if you have that, then you will say that area, in fact, even without doing that, how do you find the area of a trapezium? The area of a trapezium, you simply add the two heights. It's like you imagine that this thing has been flipped over, the same thing. Then the area becomes half of, what is that? X there, X, and you multiply by the sum of the heights. So basically, you are finding the average height there, and then you found the area of a trapezium. So that would be how you get that one. And let's take an ad break time.
All right,
okay?
let's do that. Mindsetters, keep on talking to me on the page. I'm loving what's happening. I want to say thank you to Michael, Sianella, and Nolita. You've been scarce, but you're here anyway. But guys, keep on posting on the page. Let me know what you guys are thinking. Just want to say also, Samuel, I see you. But yes, keep on posting and win these awesome, awesome prizes. But for now, we're going to see you after this ad break. And welcome back, Mindsetters. Hope you had a nice little break there. You went and did whatever you had to do. You went to grab some juice. You went to go get a snack. Whatever you had to do, now you're here, you're paying attention. Make sure you do not disappear. Yes. Now, actually, we had a question come in, Mr. E.T., from Michael. Michael wanted to find out. Okay, he has a question. He asked, determine the volume of the surface area of a sphere with a sphere radius of 30 centimeters and the hemisphere with a volume and diameter of 50 centimeters.
All right, so in both cases, he's looking for the volume,
Okay.
isn't it?
Yeah, pretty much, if I'm not mistaken, yeah.
Okay. Now, if
Oh,
you
no,
have
he
a-
says, yeah, sorry. He says, yeah, determine the volume and surface area.
Okay. So 2 questions, what's the volume and what's the surface area? Okay, so in both cases. All right. Yeah, you've been given the, fortunately with the surface area of a sphere or hemisphere, there's only one variable that you need to know, just the radius. And all you have to know is how does the formula look like. Usually they will give it to you. Let me start, if I split this area into 2 there. This side, my radius, you said it's 30 centimeters. And if I want the volume, again, the equation for the volume, we said it's 4/3 pi r cubed. As you can see, the formula has got only one thing, one unknown, which is the radius. And he just gave it to me. So all I'm going to do is substitute that. So the volume of a sphere, complete sphere will be 4/3 times pi multiplied by 30. The result is going to be centimeter cubed. All right, and that is 30 cubed, by the way. All right, where is my calculator? If I can help you quickly there. You said 4 times pi, where is pi, All right, 4 pi, shift pi, 4 pi times the radius. Our radius is 30, we multiply by 30, and we raise that to the exponent 3, and divide all of that by 3. And my calculator tells me I will have 36,000 pi. All right, so this will be equal to 36,000 pi, but this is now centimeters cubed. Okay, so that is the volume, but of course, if you don't want to put pi there, you're going to, pi is basically 3.141. So you multiply this by that and get even the, so this is actually a rough idea of what the volume will look like. All right. So if you wanted the surface area then, extend that. The surface area of a sphere, surface area for a sphere, we said it's given by 4 pi r squared. There again, you know r. R is the only thing that you need to know there. Then you can determine the surface area. This becomes 4 pi multiplied by, our radius is 30. We then square it. Our area must be in centimeters squared in that case. All right. So what do we end up with? My calculator tells me, what did I say we have here? Let's see. This is 4 pi times 30 squared. So that is 4 multiplied by shift, right, pi. And then we multiply that by, if I can just move this to there. So then we multiply by 30 squared. There's the area that we have, which is 36. Let's get my pen there. 3,600 pi centimeters squared. Okay. Where is that? Okay. So is that what I had? Let's check again. 3600 pi. Yes, so that's what you have. Okay, so that's for a full sphere, the full volume and the full surface area. So if you wanted to paint, the whole of that surface, you know how much, you must prepare for. All right, so now you want the same quantities for the hemisphere. Diameter, 15. Now, here is something you have to know. A diameter is always 2 times your radius. So this is 2 times r, which means our radius in this case will be 15. R will be equal to 15 over 2 centimeters. Okay? The same quantities. Now, you can imagine if you've got a full volume as 4 pi r cubed divided by 3, you just need half of that. So all you have to do is put a half in front of that. So the volume of a hemisphere will therefore be half. The normal formula for a volume of a sphere is 4 over 3 pi radius to the 3. So that's what we are going to have. And surely you can cancel out there immediately. You can see that goes 2 times. So what do we have? We have that our volume is going to be 2 over 3 times pi multiplied by, now our radius is actually 15 divided by 2, and we cube that. Okay, if I take my calculator, that is going to be, clear that, we're going to have 2 times shift pi, and we multiply that by 15 over 2, it's 7,5. So 7,5. Okay, you said multiply by. Let's see.
All right, Mr. Iti, maybe just check
Yeah.
if you hit in the corner there.
Okay.
Yes, close that one. Oh, just
right.
try again.
Yes, now it's going to work. 7.
Oh, you need to use your finger for the calculator. So if you just close that ink layer,
All right.
there we go, and then yeah, you can use your finger to calculate.
Okay.
There we go.
7.5. Again, then I'm facing a challenge again with this, technology time. Okay, divided by 3. All of this must be divided by 3. And what do I get? I get, let's just see if we can get this actual number. The actual number that I'm going to get there, that's 883. All right. So it's going to be 883. Right, let's get a pen there. 883 and some odd, fraction after the comma. So that will be in centimeter cubed. So go get the right value. I mean, if you can take it to say 2 decimal places, that would be enough. All right, so that was the volume. Let's move on to the surface area now. We said the surface area of a full sphere is 4 pi r squared. Now, if it was a shell, I would say you cut in the middle and now you have an open base. But if it was a solid, I will say you still have a surface area at the bottom to account for. All right, so let me do both. The surface area, if I have an open base, will be simply the normal surface area, but half of that. Half of 4 pi r squared. That would be if you've got an open base. All right? And if I can maybe just work it out quickly. All right. I'm sure you can actually go work it out. I've lost my calculator again, Ty, but don't worry. So you would work out, that expression if it was an open base. If you had a situation where it was a solid, you now have an extra surface at the base, which is circular. And your surface area, if it was closed base, let's call it that. Or we could have said the case of a shell and the case of a solid. So a solid gives you that extra, surface. All right. So in this case, we would have to have the same area, which is 2 pi r squared for the curved section of the sphere. So that would be 2 pi r squared. And you would have to add to that the base area, which is simply pi radius squared. And 2 pi r squared plus pi r squared is simply 3 pi radius squared. Go and substitute the value of r, and yeah, a bit of exercise for you and see what you get. All right, I've answered that question. I think I'm happy the way I answered it.
All right.
And I hope, what's his name?
Michael.
Michael, I hope he's happy with it.
Yeah.
All
Michael is fine with it.
All right.
Yeah.
Is there another one?
I'm looking through the page, and no, I think that was the only one.
All right. All right. So now let's carry on with truncating some of the surfaces. In fact, what Mayako has given me here is another example of a truncated volume. It's just that this one we cut it right in the middle. We took our sphere, we cut it with a plane in the middle. That is truncating basically. And if I move on, last week I was talking about surface areas, and I told you how we can look at areas as either simple areas or compound areas. So compound areas, I said that's when to get the area that you're looking at, you need to have a combination of bits of areas. It could be a triangular area added up to a square area like we did with the net. Okay, what about a volume? Can't we do the same with that? Yes, of course we can do that. Imagine a case where you've got a cylinder and it's got a hemisphere. Let me take my Ecos example. We've got a hemisphere, right at the top of that cylinder. And let's say we want the volume of that and even the surface area. The scenario I'm painting here is where you have a cylinder with a hemisphere at the top. There is your hemisphere. And that's your cylinder. I'm sure many of you are saying, oh, well, I've seen many of these shapes. Either the dustbin at home has got a hemispherical cover, and the bottom is a cylinder. Those kind of situations. So now, how are you going to find the volume? How are you going to find the surface area? This is now compound area and compound volume. To find the total area, I will have to deal with volume number 1 and volume number 2 and take them as things that get added up to give me the total volume. Volume 1 plus volume 2. That's what I call a compound volume now. Volume 1, in this case, we are looking for the volume. Therefore, we'll take, in fact, we've already worked it out. Okay, but let me just take it from here. You'd have to say it's half of the volume of a sphere. And I would have to give you this dimension, obviously. If this dimension was, let's say, 2r, just to be consistent here, and this was just h. Okay, so the way we normally found the volume of a sphere, that's what we would do. We would say half 4 over 3 pi times the radius cubed. And to that we would add the volume of the cylinder, volume number 2, which is, again, the base area, which is pi r squared and that would have to multiply by the height. Okay. Let me just show you three-dimensional how this thing would look like. Something like that. Okay. So that's how you, that would be the volume that would be, that can fill that up. Okay. And finally, what do we have? We said, this is a compound volume, but we can also do a compound surface quickly. Compound surface, we would have to say the surface, the total surface area will be the surface of the hemisphere plus the surface of your cylinder, plus obviously if it's closed at the bottom, again you have to take note of that all the time. Cylinder plus surface area of base. Okay. I don't know if we still have time. I can run through this example, but you must tell me if we have.
I think we're out of time.
Maybe,
I think this is where we can call it a day.
Yeah, that's fine. But I mean, that summarizes what I wanted to talk about today. Shells and solids, guys, take care.
All right, so mindsetters, hope you guys enjoyed the show. Make sure you keep talking on the page, and I want to say I'm going to search through the page and find who I'm going to be sending this awesome stuff to. And I want to say thank you to Liberty, and I want to say enjoy your Heritage Day. Make sure you go out there and experience the culture. But for now, this is where I sign off and say see you next time.